Hi, welcome back to Moose and Chemistry. This is electron configuration of the element Hafnium, HF lesson. Okay, well Hafnium happens to be element number 72 on the periodic table. So let's go ahead and write a 72. Alright, and its atomic mass number happens to be 178. So I'm going to write 178 right here. So since the atomic number is 72, we're going to have 72 protons. That will give us also 72 electrons. Now what about the neutron count? Well, again, you go AMU minus the number of protons, this is the easiest way to do it, equals the number of neutrons. So you go 178 minus 72, and you get 106 neutrons. So you put 106 right there. Pretty darn amazing and snarly at the same time. So let's go ahead and clean a bit of this up here, and we're going to get ready to do our electron configurations, which are pretty fun to do, I have to say. Okay, now S can hold, of course, 2 electrons. P can hold 6 electrons. D can hold 10 electrons. F can hold 14 electrons, right? And we're going to use the off-ball principle, which says to fill the lower shells first before you fill the upper shells, right? And we're going to use the diagonal rule and follow the arrows and the slides to get it accomplished. And we're going to do it until we run out of electrons, which is 72 electrons. So we're going to go 1s2. Okay. Then we go right here. That would be 2s2. Pretty amazing so far. Then 2p6. Okay, we're on our way. 3s2. 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, and last but not least, 5d2. And then we run out of electrons. Okay, pretty darn snarly. Okay, now we're going to do orbital notation. Now, orbital notation uses Hund's rule. Hund's rule says you have to put a sub arrow, you have to put an up arrow in every suborbit before you put the down arrow, right? So look at this, 1s, watch this. Up and down. 2s, up and down. And like in other videos, I said, watch this classic one. 2px, 2py, 2pz. Hund's rule. Put an arrow in every suborbit going up, and then before you start the down arrows. 4, 5, and 6. And that's Hund's rule right there, guys. So let's keep on going. And we'll just keep filling in this order. Notice how I filled them in? Up, 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 and then down, down, down. See? And then, of course, the S are up and down. 1, 2, 3, 4, 5. And then you go 6, 7, 8, 9, and 10. Okay, pretty easy. 1, 2, 3, 4, 5, 6. Up and down. See how easy that is? 1, 2, 3, 4, 5, and then go down. 6, 7, 8, 9, and 10. 1, 2, 3, 4, 5, 6. Up and down. And count 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 5d2. 1, 2. That's pretty easy. Okay, now our nearest noble gas to Xe, of course, is going, HF is going to be Xe. I'm getting ahead of myself. So we're going to put Xeon right there. This is noble gas notation. It's kind of like a shorthand version of electron configuration. And we know that this right here, guys, is Xeon or Xe's actual electron configuration. So we're going to put the rest of it, this stuff right here, into numerical order, which would be 4F14, 5D2, 6S2. Now, let's do our quantum notation. Pauli exclusionary principle clearly states that no two elements can have the same set of quantum numbers. Okay, now, we know that hafnium is located in the D block, but it looks like it's in period 6 going across. But remember that D is n minus 1. So this would be 6 minus 1. That would equal 5. So our value of our n value is 5. It's in the D block, so the L value, or the angular momentum, is going to be 2. It's the second one over, so that value is going to be negative 1 for our m value. There we go. And our S value, the last arrow is going up. See that right there? So that's going to be 1/2 positive. And that's it for this lesson. You guys be snarly. I will see you back here at Musin Chemistry.